All right, question number 9 says, the diagram below shows a circle where AC is a diameter, so AC is a diameter. B and D are two other points on the circle, and DCE is a straight line. Angle CAB is 28 degrees, and angle DBC is equal to 46 degrees. We're asked to calculate the value of each of the following angles, show detailed working where necessary, and give a reason to support your answer. So we're asked to calculate the value of angle DBA. So let's identify the angle. It's angle DBA, angle DBA. That's this angle here. Angle DBA. Now, what I would use to determine the size of that angle is the fact that this angle is 90 degrees. So I would say to the examiner that angle DBA would be equal to 90 minus 46 degrees. It would be 44 degrees. And the reason for that is that angle ABC is equal to 90 degrees, and that angle ABC is an angle in a semicircle. So the angle in a semicircle equals 90 degrees. The line AC is a diameter, and the diameter divides the circle into two halves. The angle in a semicircle, which is angle ABC, is equal to 90 degrees. So if ABC is 90 degrees and part of it is 46, it means that the other part must be 44. Angle DBA is 44 degrees. So this angle here is 44 degrees. Next, we're asked, so the reason that I just wrote up there in the right, after the bracket, you could put the reason in this space here. All right, next we're asked for angle DAC. So let's identify angle DAC, angle DAC, that's this angle here. All right, now angle DAC is equal to 46 degrees. The reason for that is that angle DAC and angle DBC are what you call angles in the same segment. And angles in the same segment are equal. So notice they have the same starting point and the same ending point on the circumference. They both start at D, and they both end at what? C. And the both angles are formed at the circumference in the same segment. So whenever you have angles like that, those two angles are equal. They're called angles in the same segment. So I would say to the examiner that angle DAC is equal to 46 degrees. I would tell him that angle, I could say that angle DAC is equal to angle DBC is equal to 46 degrees. They are angles in the same segment. Angles in the same segment are equal. Next, we're asked to find angle BCE. Let's identify that angle. Angle BCE, that's this angle here. Now, to find that out, we need to observe that ADCB, ABCD is what you call a cyclic quadrilateral. All right, that didn't work so well. ABCD is what you call a cyclic quadrilateral. trying to get this thing to recognize the shape. It does. So my red quadrilateral is what you call a cyclic quadrilateral. Now, a cyclic quadrilateral is a quadrilateral that is drawn inside of a circle, such that all four vertices are touching the circumference. So all four vertices, A, B, C, and D, are touching the circumference. Therefore, A, B, C, D is called a cyclic quadrilateral. Now, this angle here is called the exterior angle of a cyclic quadrilateral. And this entire angle here is called the opposite interior angle. Entire angle is called opposite interior angle, and the angle BCE is called the exterior angle. And the exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. So I would say to the examiner that angle BCE would be equal to, was it 46 plus 28? 46 plus 28. I'm guessing that that would be what, 70 what, 4? Is equal to 74 degrees. And I would tell him that the exterior angle, I would tell the examiner that the exterior angle, which is angle BCE of a cyclic quadrilateral is equal to the opposite interior angle. And that angle is, the opposite interior angle is DAB. So that is angle DAB, which is equal to 46 plus 28 degrees. All right. So I got my answers, gave my reasons. Move on to the B part of the question. Just looking, ensure we're not missing anything. B part of the question says the diagram below shows a quadrilateral PQRS where PQ and RS are parallel. So PQ and RS are parallel. So that means PQRS is a trapezium. Because if you have a quadrilateral and one pair of opposite sides are parallel, it's a trapezium. We are told that QS is 8 centimeters, angles are 90 degrees, one angle is 82 degrees, one angle is 30 degrees. We're seeing all of that. We're asked to determine the length of PS. We're asked to determine the length of PS. We could call it X. Well, this angle here would be equal to 60 degrees. Or if you don't want to go 60 degrees, if it's not obvious to you, it should be obvious that this angle is equal to 30 degrees. And the reason for that is that the two angles are alternate angles. And remember, alternate angles are Z angles. So I could say to the examiner that theta is equal to 30 degrees, alternate angles. Now, this side X is opposite to the 30 degrees, and QS is the hypotenuse. Now, the trig ratio that includes opposite and hypotenuse is sine. So I'm going to say sine of theta is opposite X over the hypotenuse 8. Sorry, theta is 30 degrees. So the sine of 30 degrees is equal to opposite X over the hypotenuse 8. Now, if I have one fraction is equal to one fraction and I want to get rid of the fraction, I would cross multiply 1 times x is x, is equal to 8 multiplied by the sine of 30 degrees. Now, x is PS, is equal to 8 sine 30, which I think is 4 centimeters. So PS is 4 centimeters. All right, next we're asked to calculate the length of Q, or PQ is up here, so I could call it Y. Y would be the adjacent side. So I could use cosine and say that the cosine of 30 degrees is equal to adjacent Y over the hypotenuse 8. Cross multiply and we get Y is equal to 8 cosine 30 degrees. So Y, which is PQ, now 8 cosine 30 to is 6.93, is 6.93 centimeters, and this is to 2 decimal places or to 3 significant figure. Next, we're asked to calculate the area of PQRS. We're asked to calculate the area of PQRS. So I'm guessing here is where cosine rule would come in. You didn't have to know cosine rule. You could have done it. You could have done it another way, but sine rule would be the easiest thing to find out. Because remember, in order for me to calculate the area for trapezium, I need the length of the 2 parallel sides and I need the height. So I have the top side, PQ, which we just got is 6.93. What we don't have is the bottom side. Let's call it Z. So to find that, I'm going to use sine rule. Now, this angle here would be 180 minus 82 minus 30. 180 minus 82 is 98. 98 minus 30, I think this angle is 68 degrees. So for those who know sine rule, you're going to know that the sine of, so if I wanted to, I could call this alpha. And I could say that alpha is equal to 180 minus 30 plus 82. And that this is equal to 68 degrees. Using sine rule, I want to find Z. So Z over sine 82. So I'm going to go using sine rule, Z over sine 82 is equal to 8 over sine 68. Doing my sort of like half cross multiply, I'm going to get that Z is equal to 8 sine 82 divided by the sine of 68. So Z here comes out, Z, which is SR, the bottom side of the trapezium, comes out to be 8.54 centimeters. So now the area of the trapezium is equal to a half A plus B, which are the sum of the parallel sides, times the height, which is the perpendicular distance between them. So it's a half, 6.93 plus 8.54 times the height, which is 4 centimeters. So obviously, This I have, this is 2. And if I put this in my calculator and press equal, I'm going to get an area of 30.9 centimeters square. The area of the entire trapezium is 30.9 centimeters square.